Okay, so we built the Chesapeake Bay Bridge span, and we built a couple parts of that, and we looked at what would happen as we tried to support it. And as we went through and put in different parts to the bridge, we saw that different parts of it would support differently depending on the piers that were underneath it. So we had one group who had built a bridge, and it came across and went like this. We had the bridge here, we had a support there, and a support there. We had a second bridge that came in and went across this way and had a third support in the middle. And you saw that as you applied a load to it, that part of it would come down and part of it would not. So you can see that we're supporting it, and these beam bridges are, if they're unsupported in the middle, can only take so much weight. And that's one of the things we need to deal with, and one of the things we need to look at is that what can it handle, and what do we need to do to make the bridge stronger. One of the ways that we also saw we could make bridges stronger was with arches. And as we looked at it, we could come in with an arch, and as it comes this way, instead of the bridge just wanting to push down, as we put a load down on the top and we push here, instead of the bridge just wanting to collapse straight down as our first bridges did with the Chesapeake bridge, the weight would be distributed outward to the outsides. Now the problem with this is that the bottom of the bridge, just like with the other, wants to push out. So you have to put in what's called an abutment on the side, something right here to keep it from pushing out. And you'll see these, you see them in cathedrals, you see them on all kinds of other structures. When you look at the big cathedrals in the cathedrals in Europe, they actually have these big huge pieces that come out here on the side. They're called flying buttresses, and that's what keeps the arches that keep the big span, the main span of the cathedral, from pushing the bottom out, and the bottom piers come flying outward. There's those flying buttresses, and they keep all the force moving downward and let everything push downward, as this keeps the feet firmly planted in the ground and firmly planted where it is. So we've seen a little bit what happens and what goes on. Also want to look at some of the forces that occur in these bridges as we go through them. So we have our bridge, and if we have, we're going to draw it a little bit thicker. We've got a thicker bridge so that it'll stand up. And this is our bridge. We're going to break it, divide it into little pieces. And this is our bridge with no load on it. So we've got our support right here. Here we've got no load. But as soon as we start to load it and we put a load on it, we're going to see that it wants to sag. And I'm going to exaggerate it just a little bit. Put our feet in, but now it's starting to sag. So as we put our load on this, load comes in right there, we'll see that this top part is starting to push together. This is compression. So the top of this bridge, this beam, is under compression, but the bottom is pushing away. The bottom of it's under tension. And this creates an interesting problem with bridges, is that they're both under compression and tension at the same time, even though that this is a solid piece, solid structure. As you put the load on it and it starts to sag, the top of it's under compression, the bottom's under tension, and you have to build for that, and you have to plan for that. You have to plan for this part of it to pull away. And as you construct your bridges and the joints, you need to make sure you take that into consideration, that these are going to pull away from each other. And there also, you see that it's pulling away right here. You keep contact here, but this part wants to pull away as well. So we have a tension here as well. Let's go in and look at what happens on an arch. Here's our arch bridge, and we're going to break these pieces, break it into pieces. And this last piece right here, this is called the keystone. This is the one. And when you put your load on that, the keystone actually pushes everything and moves all of this. All of this here is under compression. You've got a shear force out here that wants to push these two away from each other. And that's a shear force because the parts are moving in opposite directions from each other. And this is pushing up on your abutments. So the whole bridge is under compression. You notice that it's not under tension now, because these pieces are also built at slight angles. They're not perfectly square, they're actually angled. so that they can keep under compression both on the inside of it and the outside. So that's one of the advantages of the arch, is that it is completely under compression the entire time. So when designing a bridge or structure, engineers are going to try to eliminate a combination of compression and tension so that it acts together on a structural member, because that leads to the bending when you get both compression and tension together. That results in member bending, could break the whole structure. Alright? Materials are strong or weak when acted by tensile stresses or compressive stresses. So by designing your structure so that members are only under compression or under tension, bending effects can be reduced. So that's what the arch does. It puts it only under compression. And then finally, arch bridges are stronger than beam bridges because the whole structure is under compression. External load forces acting on the arch are dissipated and move along the curved ends towards the bottom, from there to the supporting sides. The reaction of the supporting sides is to push back against the arch, creating a resistance that's transferred along its length. All parts of the arch bridge are therefore under compression, from the weight of the bridge deck pushing out along the curve of the arch and from the resistance of the sides pushing back. Tension, by comparison, is a very minor force in the arch and even on its underside. Early arch bridges were made from stone, a material that's strong under compression. Many Roman arch structures are still standing today and are made without mortar, a testimony to the inherent structural strength of the arch. The only things holding the blocks in place are the compressive forces acting in the structure and the ability of stone to resist compression. Arch bridges, however, need strong supporting structures, abutments, to keep the sides in place and prevent the arch from collapsing. So, as we go through this, we're going to start looking at other structures and other ways of putting bridges together and some future bridges. We'll see you next time.